Okay, I think we can start. Hello, everyone. Welcome back to this first and hopefully last online edition of the Avogadro meeting. This is the last session of today. Again, the rules are the same as before. Again, we have 4 talks, 10 minutes each, and please ask questions only at the end of the talk. So the first speaker of this last session is Riccardo Gonzo from Trinity College Dublin. He is talking about light ray operators and detector algebra. Please.
Hi, everyone. So I would like to thank the organizer for giving me the opportunity to give this talk and present my work, which is joint work in collaboration with Andrei Pokakra and McGill. So I will talk about light ray operators, and I would like to spend some time explaining why I think they are important. So first of all, they are interesting in local operators that they naturally arise when you integrate Einstein equation near null infinity. So you have the retarded time, you just solve Einstein equation along that, and you integrate over that, and you find a bunch of these non-local operators. And moreover, they have some interesting applications. So some of them are related to event shapes properties. That is, for example, in jet physics, you have these localized jets in a particular, let's say in electron-positron annihilation, where you produce these jets. You can define not only the cross-section, but some less inclusive observables, which has some weight factor, in particular energy event shapes. And I think this can be generalized to the case of gravity. So that is also a main part of our result. And it's very important these detectors are localized in a specific direction. So we'll see what this means. And you can think at expectation values of these light ray operators at actually inserting these detectors, spatial infinity, and integrate along this retarded time. So this retarded time is the time that the detector is working, and it collects the quanta of radiation, and you get the result by insertion of this operator in a correlation function. So let's start with the definition. So for this work, we look only at R modes. So there's been a lot of wonderful works by Stroming and collaborators in the past 7 years on soft theorems and so on. And here we restrict our attention only to R contributions. There are soft contributions. We look at some of them, but we didn't look at them regarding the algebra. So let's consider a real detector with some low energy resolution and just throw away soft modes. The technical way to do that is to impose some boundary condition just to avoid some soft contributions. So the way we define that is in flat null coordinates, which I will say later what they are. We define them as some integral, so that they are light ray, so integrated along some null sheet, the retarded time on the light sheet. And TUU is the main component of the stress tensor, which enter in definition of E and K. They can be taught as some null energy density and boost mass density. So you see in the K, there is also a factor of U. So it is some kind, well, as we'll see, is related to some kind of dipole type contribution compared to a monopole of the E. We'll see later what this means in terms of the action on shell states. And for the NZ, this can be taught as some kind of density of angular momentum flux. It's a bit dangerous to talk about densities because, of course, you can define only equivalence classes. I mean, you can always have a total derivative term and get the same integrated charge. So in some sense, we define them starting from the usual stress tensor, the Hilbert stress tensor, for the case of spin 0 and spin 1. For gravity, they naturally arise from solving Einstein equation and null infinity, and basically bringing the linearized contribution of gravity on the right-hand side of Einstein equation, as you usually do. And I would like also to point to something that is only the time-time component and time-spatial component appear in this definition. There is no spatial component. This is very important for the algebra. So as, Bulwer and Deser first show for the commutation relation of stress tensor, and also later, like by Swinger, the universality is only in time or time spatial. Spatial component stress tensor are not going to be universal. So if you look for, say, universalities of this algebra, it's important that they are time and spatial components. Okay, so as a definition for the stress tensor, we take the standard Hilbert stress tensor. So we coupled our action with gravity, and we just use this formula. And then the flat null coordinates are defined as follow, so that they are very convenient for analyzing null infinity and especially for massless particles. And what happens, for example, to the phase, because to evaluate them, we use the saddle point estimate. And in particular, for the modest function of on-shell quantum field, so you have the e to the ip dot x, e to the minus ip dot x. And when you write in these coordinates, you can see that the fact that the R-dependent factor, we're taking the large R limit. These detectors are far away from the interactions. And you can see that there is this factor z minus w module square, which basically localized completely at zz bar, which are related to the coordinate position coordinates, to the momentum coordinates. So there is some kind of locking, which is very well known in asymptotic symmetries framework between the momentum and spatial coordinates. And also, please notice that the time component of the momenta, the energy, is not the standard energy factor. We also derive for the gravity case like the standard energy factor from bonding coordinates, but in flat null, you get some kind of retarded energy factor, like the light cone energy, basically, which is a bit different, but it doesn't change the result. Okay, so these are the coordinates in the simplest case for the stress tensor, TUU and TUZ, which are the one appearing in the light ray definition for the scalar. And we consider self-interacting massless scalars without derivative interaction. Actually, well, at non-infinity, of course, there is some scaling of the fields at infinity. So higher derivative usually drop off. But the point of showing this expression and say without derivative interaction is that if you do the same calculation for a light sheet in the bulk, so we consider for the moment definition I gave before, where for the light sheet, where these light ray operators are defined and non-infinity, but you can do the same for a light sheet in the bulk, and the same simplifications happen. So if you look at the algebra, you should expect kind of the same property. And for this stress tensor, we use the saddle point expression using the large R limit, as I explained before. There is a beta technical point on the spatial derivative of the field, which we took care of, and it's basically just it's different. Usually, it's different. Like to take the saddle point in the even-shade literature, they were taking the saddle point of the full stress tensor, but you can take the saddle point of the single quantum fields. And the result is not going to always agree, taking saddle point of the full expression or the single basis of expression. I think it's more useful to take saddle point of the single field because you localize on the point particle expression, and that's what we want. So when you plug in the values in the light ray operators, that's what you get. So you can see from this E, which is basically some kind of NX operator at infinity. It's not the NX operator because there is a limit R goes to infinity, I showed before. So there is a limit R squared goes to infinity, so you pick up only the leading component. And in this case, you get this delta function, but it's very similar at the end. The expectation values are still positive definite. So that's also something important. The K, as you can see, there is a derivative of delta omega minus, which is something we found a bit strange, but actually it works for the algebra, and it makes clear how the algebra that other people derive, like namely Cordova and Shao for the conformal case, arise for this part of the algebra. For the NZ, you can see the expression. So there is a derivative in between the two creation and annihilation operator. And that's expected if you look, for example, Zuber, the total angular momentum charge. You can say the same operator between B dagger and B to get the right algebra for the angular momentum. And note that the action of this NX operator at infinity and on-shell state basically gives the sum of energy in a particular direction. And this is the connection with energy even shapes. which we'll do not only for scalar and spin 1, but also for spin 2. There is, as I said, also this is a positive definite. If you insert in a completeness relation, like you will get the square of the modulus of the, since this is just a weight factor, the square modulus of the amplitude, so that is positive definite. And then you have the integration left over on the phase space. The non-trivial part is that these are infrared finite, so this non-trivial part. Okay, so the scalar light ray algebra that we got is as follows. And basically, we got something consistent with the complexified Cordova-Shaw algebra, and we checked explicitly that for the first 5 commutators we get this, and the last one is also consistent if you take into account the different components of the stress tensor. Basically, how they arise from the light concordance in the bulk and the coordinates and non-infinity. Just to conclude, let's look at results for spin 1 family. It doesn't change much, except that there is a spin term, which is the helicity term. So there is this sum over helicity. We use a canonical commutation relation. And this is consistent with the point particle structure of the stress tensor, which was shown, for example, in the paper on gravitational memories. And for the light ray operators for gravity, we solve Einstein equation in null infinity. And there is a convention, so you need to pick up a convention. There are some different conventions in the literature. And we found that the one by Pastersky, Strominger, and Ziboydev is the most natural one. And it gives the same type of expression as spin 1. The curious fact that the orbital spin algebra, which is the additional piece you have to compute, seems a bit problematic and needs some kind of further investigation. So to summarize, we interpret these light ray operators as localized detectors, and we provide explicit expression for the armor contributions. And we care about the reaction of Jean-Shell particle states. The algebra we found is consistent with the complexified Cordova-Shaw algebra, and more analysis is needed for the orbital spin contribution. And we have defined also this gravitational even shape from the saddle point estimate of the gravitational N operator at infinity. And thank you.
Thank you very much, Riccardo. Are there questions? Comments? Maybe I have one, more technical one. So you mentioned about the space-space components of the stress tensor in the beginning.
Yeah.
So what do you mean? It doesn't appear, or it is? So you mentioned the non-universal. Can you elaborate more on that?
Yeah. So if you use so if you look at how to derive this commutation relation between a stress tensor, since it is conserved, you can derive that from swing direction principle, let's say, but not for special components. There are some leftover components that are not fixed, and these they don't appear in the light ray. So why should we expect some universal in the light ray algebra at all? I mean, in general, I mean, there are different theories, and we don't expect something universal. But the reason why we can expect something universal in this case is because these space-space components don't appear at all in the definition.
I see.
Yeah, this was, well, yeah, started with the work on Bulwer and Dazer, but it was revived quite recently by Wang. I think it was his paper on this.
Thank you. More questions?